In this video, we're going to look at adiabatic processes in contrast to isothermal processes. So the definition of adiabatic is pretty simple. It's just a process with no heat. So the heat during a process is going to be 0. So that simplifies our equation for the change in energy, because that's going to be delta U. Change in internal energy is just going to be Q plus W. And if we know that Q is going to be 0, then that means that our internal energy change is going to be equal to the work. Okay, so when we looked at internal energy of an ideal gas, for a monatomic gas, that is going to be 3/2 nRT. So we know that if we have a constant number of particles, the internal energy only depends on temperature. So if we have a change in the energy, then we are going to have a change in the temperature. So we want to be able to calculate for an adiabatic expansion or compression of a gas, what is the final temperature if we're given the initial temperature, or vice versa. Okay, so if we look at the derivative of energy with respect to temperature, du dt, at some constant volume, then that's going to be, well, if we have a constant number of particles, then it's just going to depend on T, so it's going to become a total derivative there. And that is just going to be 3/2 nR. But this derivative here is also equal to the constant volume heat capacity. So we're going to have this CV here. So we're going to have that if we multiply both of these sides here by dt, we're going to have that du equals CV dt. Okay, so this is going to equal also the infinitesimal change of work as we go and change in our process here of expansion or contraction. So we know that the work done during an expansion or a reversible expansion or compression of a gas is going to be minus nRT log final volume over initial volume. And we know that the derivative of that, or the infinitesimal of that, our dW, is going to be minus nRT over V dV. So the amount of work which occurs during an infinitesimal volume change is just minus nRT over V. Okay, so we have these two related here. So we have that we have our relationship between the work and the temperature now, and thus the energy for our expansion. So we're going to have this line up here, CV dt. The heat capacity times change in temperature gives us our change in energy. Our tiny amount of work that's going to get done during that same process is going to be minus nRT over V dV. So now we're going to integrate both sides. We're going to integrate this side with respect to temperature and this side with respect to volume. So we're going to integrate from the initial to final temperature for CV dt there. And we're going to integrate over here minus nRT over V. Sorry, I need to include the V on the inside there. VI dV over V. And I should have put this T over there before I did that. So let's just go ahead and fix that. We're going to cancel out that T and we're going to put it on the denominator there. Okay, so we got that T on the denominator there. That canceled out there. Okay, so let's do both of these integrals. The integral of a constant times 1 over T with respect to T is just going to be the log of T. And from initial to final, it's going to be log of T final minus log of T initial, or log of T final over T initial. And that is going to be multiplied times CV. And that is going to equal minus NR. The integral of dV over V with respect to V is log V. And same thing as on the left side, we have log of V final over V initial. Okay, so we got two logs there. Two more simplifications we can make. The heat capacity divided by the number of moles gives us the molar heat capacity. So we have that the CV bar equals CV over N. So that's the molar heat capacity. And we also know that we can change the sign on a logarithm by flipping its numerator and denominator. So if we make this V initial and this V final, then we can get rid of that minus sign. So taking those two facts into account, we can get that log of T final over T initial times CV bar cancels out the N, and we're going to divide by the R as well, equals, we cancel out the minus sign by flipping the numerator and denominator, log of V initial over V final. Okay, so to get rid of the logarithms, we're going to do e to the power of both sides. So e to this, e to that. That's going to get rid of our logarithms. And our final result we're going to have is T final over T initial to the CV bar over R power is going to equal V initial over V final. Okay, so they're related by kind of this inverse transformation there, and also this power depending on the heat capacity. But there's another nice simplification you can make, because the value of this constant volume heat capacity has a nice simplification here. So CV bar is going to be 3/2 R for an ideal gas which is monatomic. It's going to be 5/2 R if it's diatomic. If I can spell diatomic, let's try. D-I-A-T-O. Okay, got it. And 6/2 R, or 3R, for a nonlinear polyatomic, such as water, methane, benzene, etc. So what you get here is T final over T initial to the power of either 3/2, 5/2, or 3 equals initial volume over final volume, because the 3/2 R cancels out with the R there. So we get TF over TI to the 3/2 equals VI over VF for a monatomic gas. Plug in your favorite kind of gas there, and you'll get whatever nice closed formula you want. And again, we need to remind ourselves that this is for the adiabatic reversible expansion or compression of an ideal gas.